So welcome to this PNS course on processing in memory. Thank you very much for joining. Our course, as I already said, is titled PNS on processing in memory for short. For long, it's exploring the processing in memory paradigm for future computing systems. In this next slide, you can see the information that you can find in the course catalog about this course, also a link to the course catalog. And if you take a closer look at this description and the objective of this course, you'll see that we talk about data movement between the memory units and the compute units in current computing systems, and how costly this data movement is. As an example, 62% of the total system energy for consumer applications is spent on data movement. This is what we call the data movement bottleneck, and it's essentially the main issue that we are going to try to solve in this course. This data movement bottleneck affects many important workloads these days, like machine learning, computational biology, graph processing, databases, video analytics, etc. And you will see some examples of these workloads over the course of this semester. And essentially, to solve this data movement bottleneck, or to overcome this data movement bottleneck, it's necessary to do a paradigm shift in the way that we design computing systems. The key idea is going to be placing processing elements closer to memory or even inside memory. This is what we call processing in memory. If we take a look at this slide, this motivational slide about the cost of data movement in terms of energy, I'm using here one slide from Bill Daly presented in HiPeak 2015. You see that the memory accesses consume almost 3 orders of magnitude more energy than a complex addition, for example. We will go back to this slide later, but first of all, let me state what are the goals of this PNS course. As I said before, please feel free to stop me anytime if you have questions about the course logistics that we are going to present today, about the Safari research group and our research lines. And finally, I will give a brief introduction to processing in memory, and in later lectures we will continue elaborating on many of the topics of the processing in memory topics that we are going to start covering today. Feel free to ask questions. Also, for anyone watching the lecture in YouTube, feel free to ask questions as well in the YouTube chat. I'd be glad to read them and answer if they really make sense. So, contents of this course, we will introduce you to the data movement bottleneck, which is a major threat to high performance and energy efficiency of current computing systems, as we are already explaining. You will learn what are key workload characteristics that make these workloads more prone to the data movement bottleneck, and we will review traditional approaches to alleviate the data movement bottleneck, but also, and more importantly, you will get familiar with the new research proposals and real systems that represent processing in memory solutions. And as part of this course, you will have to do a hands-on project. These projects are the ones that we are going to offer to introduce in our next meeting. Some of these projects will be, different topics and different goals, like analyzing workloads, programming real PIM architectures, or simulating new PIM proposals, for example. Processing in memory is not something new, but it's something that starts becoming a reality these days. But if you go to the literature, you will find papers that are more than 50 years old, like, for example, these cellular logic in memory arrays from William Kautz, or this other one that is contemporary, titled A Logic in Memory Computer from Harold Stone. So it's been more than 50 years since these proposals, until one company released, designed, fabricated, and started to commercialize the first real-world processing in memory architecture. And this company is a French company called AppMem. And what they have done is fabricating DRAM memory in standard DDR4 DIMMs, where inside each of the chips we don't only have memory, DRAM memory arrays as usual, but also small processors or small general purpose cores that are called DRAM processing units or DPUs, and can be really useful and suitable to accelerate some important workloads. Here you have a picture of the ABMEM DIMMs with the different PIM-enabled chips or PIM chips. And here you have another picture of a large system with more than 2,500 DPUs, or these small cores that I'm mentioning inside the DRAM chips. In this picture, you can identify 2 CPUs. It's a dual socket system that has conventional DRAM memory that is still being used as the main memory of the system, as you see in this scheme here, and also other DIMMs, the ABMEM DIMMs that represent this PIM-enabled memory. This architecture is already capturing a lot of attention from industry, from academia. We have been so lucky that since a while have been working with this architecture, programming it, analyzing it, and you guys are also going to have the opportunity to do it if you are interested on this. And as I said, it's capturing a lot of attention, including ETH News. This is something that has been released today. They talk about our work on processing in memory, and in particular with the ABMEM PIM system. It's a very nice and easy reading to start learning about processing in memory. But if you want to learn more and many more details about this processing in memory architecture, I can recommend you our long paper that is already available in arXiv. If you don't have time to read the whole paper, you can definitely read the shorter version of it that we published at the end of last year, or watch one of the different lectures and talks that we have given about this architecture. And actually, as you can imagine, this architecture is going to represent some of the main contents of this course as well. So for sure, you will learn more about it in later lectures. But this ABMEM company is not the only company that is starting to fabricate and commercialize processing in memory systems. About 1 year ago, Samsung announced their first processing in memory system, PIM-DRAM or HBM PIM, that is based on the fast, the high bandwidth HBM2 memory, and it's targeted at artificial intelligence applications. What essentially Samsung did is using HBM memory, which is a 3D stack memory, as you can see here, composed by multiple layers of DRAM, multiple DRAM dies, and some of these DRAM dies have been modified to incorporate some processing elements inside them. You're going to see more clear picture in the next slide, but here you can already see what are the type of operations that these processing elements are able to execute. And as you see, multiply, accumulate, and multiply, add, which are key operations for artificial intelligence and machine learning workloads. Here you see another view or a view of one of these DRAM layers that compose the HBM2 memory or the HBM PIM proposal by Samsung. As you can see, some of the cells of the DRAM cells in the banks have been replaced by these PCU blocks that are the compute units, the execution units that can perform multiplication, addition, etc., for machine learning workloads. And it's not the only proposal from Samsung itself. Also, we learned last year about this AX DIMM, that is a DIMM-based system. It's different from the previous one in the sense that instead of modifying the DRAM layers themselves to integrate processors, as for example, ABMEM or the HBM PIM from Samsung do, here what they do is placing the compute units on the same DIMM as the DRAM chips. And they have shown nice, interesting, I mean, pretty good, interesting, and interesting results for recommendation systems where they compare a baseline system with an AXTIM system where some of the original DRAM DIMMs have been replaced with these AXTIM with processing capabilities. And here you see a picture of this prototype that they use for their study and for their analysis. And also from another major DRAM vendor, SK Hynix, a couple of weeks ago, we learned about their first real processing in memory system, accelerator in memory, that is using, in this case, GDDR6 DRAM memory, and it's in principle suitable for machine learning, high performance computing, big data computation, and storage. In later lectures, we will talk more in detail about all these processing in memory architectures and proposals from different actors in the industry. And when we finish this course, you will have learned a lot about processing in memory, because these about computer architecture and processing in memory, because this PNS, this course is aimed at improving your knowledge in computer architecture and in processing in memory, also improve your technical skills in either parallel programming for processing in memory architectures or computer architecture simulation. You will improve your critical thinking and analysis, essentially because you are going to be doing research with us, and you will have the opportunity to get familiar not only with the specific topic that you work on or the specific research that you do, but also you will get exposed to other research directions from our group. And finally, you will also improve your technical presentation skills, because you will have to present your work in front of our group at the end of the semester. So, summarizing, the key goal of this course is to learn how to overcome the data movement bottleneck by programming, benchmarking, and exploring different designs of the processing in memory computing paradigm. You already know this, but I have to tell you again the prerequisites of this course. We assume that you have good understanding of digital design and computer architecture. Here I place a couple of links to last year's course of Professor Mudlu's course on digital design and computer architecture, spring 2021, and also the website for this semester where we are now, or Professor Mudlu is delivering the lectures now, and we upload videos and slides to the website. So these two can be a very good reference for you whenever you need to go back to some of the knowledge that you already have on digital design and computer architecture. Ideally, or you should have familiarity with C and C++ programming. I don't think that that will be a problem with for anyone. And if you also have some experience with FPGA implementation or GPU programming, that's going to be pretty useful for sure as well. And what we expect from you is that you have an interest in future computer architectures and computing paradigms, are interested in discovering why things work or do not work, and solving the problems, and also making systems, computing systems, more efficient and more usable. Now let me introduce a little bit our research group, Safari Research Group, and I would like to start with Professor Mudlu, who is the leader of this group. Professor Mudlu is a professor at ETH Zurich since September 2015. Here you can see, find a link to his website and also his email address in case that you want to contact him. He has many years of experience in research and teaching in computer architecture, computer systems, hardware security, bioinformatics, and all aspects of them. The rest of the team is me, who are the lead supervisor in this course. I think I didn't really introduce myself. My name is Juan Gómez Luna. I'm a senior researcher in the Safari Research Group since August 2017. And I work in processing in memory, of course, and also heterogeneous systems, but in many other parts of computer architecture as well, and bioinformatics. I'm interested in many different things. The rest of the team is composed by Dr. Hayu Mao, also an expert in processing in memory. In particular, she works with non-volatile memories and how to do processing in memory using these non-volatile memories. It's likely that she will, one of these days, give you an introduction to MV and PIM, or processing in memory with non-volatile memories. The rest of the team, Geraldo, Konstantinos, and Nika, they are PhD students, and they also work on processing in memory and also processing in storage and different other aspects of computer architecture. So the only one in the meeting, I think, is Nika. Nika, would you like to introduce yourself very quickly? Say, well, what are your interests?
Yeah, sure. So yeah, as Juan mentioned, I'm a PhD student in this group, and I focus on several research topics, in particular emerging memory and computing technologies, exploring efficient system design for them, and storage systems and bioinformatics. Yeah, thanks.
Okay. Yeah, thank you very much, Nika. You guys will learn more about Nika's interests next Tuesday, when we, as I said before, will present the project proposals that we have for this semester. If you want to learn more about us, about other people in the research group, and about the research group in general, you can access our website. You have the link on the slide. It's a very large research group, more than 40 researchers at the moment. We try to disseminate our work via our, of course, our research papers and lectures, but also our website and newsletters. For example, this that is a screenshot from the most recent one, the newsletter that we published in December 2021. And we also organize live seminars with people from our group, and also other people from academia and from industry as well. They are quite frequent indeed. They essentially every month we have Safari Live seminars. We will announce some of them for sure over the course of the semester. All of them are accessible in YouTube, and for sure some of them will be interesting to many of you. The most recent one, for example, is this one, which took place on February 28th by Sean Lee, who is one of the founders of Cerebras. Startup, a company that has fabricated an amazing ML accelerator with a lot of innovations. For sure, very recommended talk. And I'm already talking about the research group, the Safari research group, and I already introduced what are the main research interests of Professor Mutlu and the Safari research group. Here you have a little bit more detail. The research focus is on computer architecture, hardware, software, co-design, bioinformatics, and all aspects of them, like memory and storage, heterogeneous and parallel systems, like, for example, DPUs and FPGAs. We actually have another PNS course on heterogeneous systems that you may have also seen in the course catalog. We also talk about we also work on the system and architecture interaction, energy efficient architectures, and also, as I said before, bioinformatics and architectures for bioinformatics and medicine. Course requirements and expectations. Attendance is required to all meetings. Study the learning materials. Each student, as I said before, will have their own hands-on project that we will start discussing next Tuesday. We expect that you participate, asking questions, contributing thoughts and ideas, and also reading any relevant papers that some of them will be required, some others will be recommended, and we will help you all the time. You will be in touch with me, and especially more, say, intensely with the supervisor that you have, the direct supervisor that you have for your project. Feel free to contact us anytime, ask questions, be proactive, and essentially take advantage of this course and learn as much as possible. You can probably do a very good job because we have many weeks, at least I think we have like 12 weeks until the end of the semester. So you have time to really do something interesting and something useful where you can really contribute something important to the state of the art in processing in memory. If your work is really good, we will help you to publish it, and we will be for sure very interested in publishing your work. So information about the course you can find in the course website is already available. We are going to upload links to the live streams. We are going to upload there the slides in PowerPoint and PDF for your reference. There are also some links to important papers and information in general about the course. There is also a Q&A forum in Moodle that you can use, but just do whatever is more convenient for you. You can ask questions during the lectures. You can send us an email after or whenever you have any question, or use the Moodle Q&A forum. And here you have a screenshot of the course, and also the link to the course and the link to the YouTube live stream. So for this first meeting, I already sent you an email with some learning materials. I hope you are already reading and watching them. So the required materials, let's say the really important ones that are going to give you some good background and some interesting introduction to processing in memory that is going to be very useful for your background in later lectures, is this book chapter, A Modern Primer on Processing in Memory, and related to it, this lecture from Professor Mudlu, Memory-Centric Computing. Then there are also some recommended material and other, let's say, introductory paper to processing in memory here, and also some lectures from the computer architecture, the advanced computer architecture course that Professor Mudlu teaches. The next meeting, as you already know, is next Tuesday. We will announce the projects there. You will have the chance to select your project or to rank the projects and let us know what are your favorite ones. After that, we will have one-to-one meetings with you in order to discuss the projects, discuss your preferences, and find what's the best fit for you. And yeah, important that you learn or study the learning materials before our next meeting, because this way you can also have already some background and understand better the type of projects that we will present. In next meetings, we will have the lectures on Thursday at 7 p.m. But you will also have individual meetings with your supervisors or mentors. You may have one, may have two. We will see depending on the project that you choose. Yeah, and the actual schedule of these individual meetings is something that you guys will decide with your mentors. So as you will see, we are very flexible, and same as you can contact us by email when you need it, you can also schedule the meeting at your convenience. In the lectures, what we will cover is different aspects of processing in memory systems, of the architecture, how to program them. We will talk about these real processing in memory systems. We will talk also about interesting and state-of-the-art research proposals on processing in memory. And at the end of the course, we will also have a meeting where you will present your work. That probably will happen sometime in July. But if you want to, start getting more and more familiar with the different contents that we will cover in the course, probably most of them were already covered in the fall 2021 semester. So you can find them in the website of the past semester. Here you see links to the YouTube recordings. You have the PowerPoint presentations. Some of these lectures will be updated, let's say. We may also have some new lectures, for example, because we will likely present some of our more recent works on processing in memory. And but yeah, in the end, I believe that the website of the past semester is a very good reference about what are going to be the contents in this semester. Okay, I am done with the, say, introduction to the course logistics, and so on. And what I'm going to do next is giving you an introduction to processing in memory. We are going to start, let's say, talking about the reasons why processing in memory is needed, or is going to be more and more needed in the near future in computing systems. And I'm going to talk about, let's say, some classic proposals in processing in memory. Let's say classic, but recent proposals as well that are or have impacted a lot of research in academia and industry and the development of these new processing in memory systems. Do you guys have any questions about the course logistics that you want to ask now? If not, yeah, feel free to reach out to me later if you want to clarify anything. Okay, let's just start with this introduction to processing in memory. The problem, as we have already mentioned before, is the data movement that is needed between the main memory and the storage and the processors. So these, either if it's a CPU, a GPU, or an FPGA. Main memory is a critical component in all computing systems, and the main memory must scale, and this scaling is not easy and is not for free. And this is affecting all types of computing systems these days, those systems with CPUs, with FPGAs, with GPUs, with other types of accelerators as well. And this happens even though if you take a look at these processors, CPUs, GPUs, etc., or maybe it happens because of that. If you take a look at these systems, you will see that a large amount of their area is already spent on memory and on alleviating the data movement bottleneck. Here you have this picture here where you can identify the cores that are the red ones, but then there are a lot of green and yellow blocks that are either memory caches like this L2 cache or L3 cache, but we also have shared memory controllers to access an external off-chip memory. So even though a lot of the space in computing systems is spent in memory or is devoted to memory, we have a big issue with the access to the data residing in this memory and this storage. So three key system trends are, the first one is that the data access is a major bottleneck, as you already know, because applications are increasingly data hungry. Energy consumption is a key limiter. I already showed you before the motivational slide from Bill Daly. We are going to see it again now, and we are also going to give you a little bit of more, let's say, motivational data or information about the energy consumption in current computing systems. And you will see that this data movement energy dominates compute. And this is especially true for off-chip to on-chip data movement. Whatever it comes from the storage or from the external main memory to the processor is going to be very expensive in terms of energy and in terms of execution cycles. And one of the key reasons why this happened, and this problem has been worse and worse over time, is because the way that the processors, computing devices have evolved has been much faster than the way that memory has evolved. And we can take a look at how memory has evolved in let's say the last 2 decades. And what we can see is that capacity has improved, of course, because we need to store more and more data in memory, also in storage. So that's why it increases. Bandwidth also increases, and bandwidth represents or means the amount of data that we can get from memory or from the storage per unit of time. This has also increased, not that much, not so much as the memory capacity, but has also increased. However, the DRAM latency is improving by very, very little. And what this means is that it takes a lot of time to access. It takes many nanoseconds, many execution cycles to access data that resides in memory. So memory latency in the last 20 years or more than 20 years has improved or has been reduced by a very little amount. And this affects many important workloads, for example, in memory databases or graph and tree processing, in memory data analytics or data center workloads. Long memory latency entails a performance bottleneck. So memory or the access to data affects the performance, as well as it also affects the energy consumption. You already know this slide. Here you can see that, for example, a 64-bit double precision operation and addition of 2 double numbers, for example, takes 20 picojoules. If you compare these to the access to DRAM, either a DRAM read or a DRAM write, you will see that this is almost 3 orders of magnitude more energy to access data rather than computing. And this is not something new, of course. It's of course going worse and worse every year, but it's something that has been observed many years ago. This is a slide from Professor Mutlu's PhD thesis. He already observed in 2003 that most of the execution cycles for several important workloads that he analyzed, most of these execution cycles, as I said, were spent on accessing memory. In this case, this was a CPU with 2 levels of cache. And as you can see here, like 55% of the total execution time was spent on solving the L2 misses, which means that you missing L2 and then you have to go to DRAM to bring the data to the processor. And this is in 2003, but probably is even worse these days. This is a more recent study from Google published in 2015, where they showed that also a large amount of a large amount of execution cycles was spent on accessing data. And here you see some of the workloads that they run in their data centers. So the problem is that data access is the major performance and energy bottleneck. And one reason for that is that the current design principles cause great energy waste and also great performance loss. And the reason is that processing of data is being performed far away from the data, from where the data resides. And the reason for that is the way that computers have, or most of the computers have been designed and built over decades, following what we call the von Neumann model, that considers that a computing system has 3 key components, one of them for computation, another one for communication, and the last one for storage and memory. So looks like something like this, right? So in the memory and storage unit, we have memory system and the storage system. Here on the leftmost side, we see this computing unit, for example, a CPU, a GPU, an FPGA, and in between we have this communication unit. And the problem itself is not coming from the von Neumann model. The problem is coming from this communication unit, and the fact that this communication unit is very narrow and provides very little bandwidth and, unfortunately, very long latency for the compute unit to access data residing in memory and storage units. So, as I said, this affects all computing systems or most of them, and is due to the need to access data that resides in memory and storage. So the consequence is that a lot of execution cycles are being spent on accessing memory, and a lot of energy is consumed as well on doing so. And the reason is the way that current systems, current processor-centric designs are built. They are grossly imbalanced systems where processing is done only in one place in the processor, which means that the data needs to move a lot between the memory and storage units and the processor. And this is energy inefficient, is low performance, and is also complex. And it's complex because the processors themselves are very complex, because over the years there have been, so the designers have been trying to find solutions to this data movement, for example, including large and deep cache hierarchies, including complex prefetchers, etc. But still, there is no way of solving the problem forever. And the systems continue to be energy inefficient, low performance, and complex. So if you look at any system on chip, for example, similar to the processor that you have in your computer, in your laptop, or in your cell phone, you will see that it has CPU, GPU, multiple accelerators, it has several levels of cache memory, and it has also a memory controller to access the external DRAM. And there is a lot of data movement between all these components. And this data movement dominates the energy consumption. For example, 41% of mobile system energy is spent on data movement during web browsing, or so the cost of an ad operation, and this is coming from a different study, is more than 100 times more, consumes more than 100 times more energy than a simple ad operation. So the problem here is that we need, or the goal here is to make compute systems more data-centric and make them processing in memory capable, which means that computing is going to happen, or at least part of the computing is going to have to happen where the data resides, or where it makes sense. Here you see another study that is from our group, published in 2018, showing that 62.7% of the total system energy on these Google consumer workloads like Google Chrome, or the BP9 codec, or I think I don't remember right now which ones. Oh, TensorFlow Mobile, and so on. You can find the details about these applications in the paper. So for all these workloads that we are using every day in our cell phones, 62.7, or in our Chromebooks, 62.7% of the total system energy was spent on data movement. So we need a paradigm shift, and this paradigm shift is called processing in memory, that enables computation with minimal data movement, computes where it makes sense or where the data reside, and makes computer architectures more data-centric or more memory-centric instead of the classic processor-centric approach. And why memory computation today? Well, the reasons we already know. It's because we need to solve the data movement bottleneck. And even though this has been explored for decades, only until now, only now it starts to become a reality, because technology has evolved enough to enable this change. And one example are 3D stack memories. I already talked before about one type of 3D stack memory, that is HBM2, that Samsung is using to build their processing in memory system. Here you have a picture of another type of, or another 3D stack memory from another vendor. This one is the HMC hybrid memory cube from Micron, that essentially, as you see, has several layers of DRAM, and at the bottom of them there is a layer of silicon that is that can be used to embed processing elements here. This is what is called the logic layer, and it can be potentially a place to put some processing elements and compute closer to where the data resides. But this is not the only innovation that has appeared in recent years and can enable processing in memory. Non-volatile memories, as I mentioned before, and we will talk about them as well in a future lecture, are another of these innovations that enable processing in memory. The goal is to achieve high performance and energy efficiency, and the way to do this is processing in memory, as I said. In principle, what's the idea of processing in memory? The idea is not moving everything to the memory. Of course, that's not going to happen. Why is that? Because we still need to have these powerful CPUs and GPUs or FPGAs to accelerate some important parts, more, let's say, compute intensive parts of the applications, but just offload those parts of the computation, those parts of the application that make sense to offload to the memory, to the processing elements in memory. So here you can see a very naive figure that shows a query that is offloaded from this could be a query in a database, and in memory database, for example. The processor sends this query, offloads the query to some processing unit residing near the memory, and this processing unit access memory. The advantage is that it has higher bandwidth, lower latency, can obtain whatever data the processor needs, and then sends back the results to the processor core. So conceptually is very simple, as you see. Practically is pretty challenging because there are many questions to answer and many design challenges to solve. For example, we need to design compute capable memory, different ways of doing it, as we are already seeing and we will see in this lecture, but we may also need to modify the memory controllers or the processor chip, or we have to create new hardware and software interfaces for the programmers and also for the processors to communicate with the processing and memory side. We may need to develop new software, new languages, maybe new algorithms as well. In the end, it's something that affects the whole computing stack, from the problem and the algorithm to the devices and almost the electrons, as you see in this slide. So this is processing in memory. There are different types of processing in memory that we are going to cover in this course, actually in this lecture already. Here you see the first example that I mentioned a couple of slides ago, the idea of using this 3D stack DRAM and taking advantage of this logic layer to put there some small processors, accelerators, for example. We will see some of these examples soon. Or we can also talk about processing in memory in some proposals that place some type of processing element in the memory controller itself. So instead of having to move the data all the way until the CPU core, you can maybe access the data from the memory controller and compute near the memory controller. And this way you avoid, for example, polluting the caches of the CPU. Or another possibility, and we have already seen one example of this, the IEDM PIM architecture from Samsung. We here place the processing elements on the DIMM. So these are just some examples. Another example that we have already seen is in some sense, let's say conceptually similar to the idea of using 3D stack DRAM and the logic layer in 3D stack DRAM. We have this admin PIM system that in this case places the processors inside the DRAM chip. And this is DDR4 memory is 2D DRAM, not 3D, but we can also do it there, or as I said before, on the DIMM as well. And then what is the type of processor or the type of accelerator that we are going to put there on the PIM side? Well, we may have accelerators or fixed function units. We can also have reconfigurable architectures. Potentially, we can have them like FPGAs, or we can have general purpose cores. If you take a look at the examples that we have in the real world already, you will see actually several of these. Actually, there are fixed function units is more or less what Samsung is doing with their HBM PIM memory that only accelerates very concrete operations like Mac. So it's not really fixed function because it's programmable, but it has a very reduced instruction set, just multiplication, addition, and some data movement instructions. There are also reconfigurable architectures. The AXT proposal, for example, has been tested on a prototype that puts an FPGA on the DIMM. So that it's one example of reconfigurable architecture for processing in memory. And general purpose cores is what we can find, for example, in the AppMem architecture. Together with this, there is one last proposal, one last way of doing processing in memory, that is what we call processing using memory. And I'm going to very soon describe what this is about. If we, let's say, want to classify, let's say, have the first classification of processing in memory systems, you can find it in the book chapter that I ask you to read, say, first important reading in this course. And here in table 1, you can already see like this distinction between processing using memory and processing near memory. And this is what we are going to talk about in the rest of the lecture. We are going to talk about what they exactly mean, and we are going to see a couple of interesting examples of each of them. The first one being processing using memory. In processing using memory, the goal is to enable computation inside the memory using the operational principles of the DRAM cells themselves or memory cells themselves, and change the memory chip minimally. Why is that important, or why is that, let's say, desirable? Because in the end, if you want to modify something that is already being fabricated, commercialized, and used in all computing systems these days, like, for example, DRAM chips, you want to modify them minimally, right? So if you want to put, let's say, a processor there, like a RISC-V core, for example, you will need to spend much more area. You will need to, for sure, take into account many different considerations that in the end will make enabling this architecture or creating this architecture a real challenge. So the idea in processing using memory is to modify the chips, the memory chips minimally, and take advantage of the way that memory itself is already working. Let's see the first examples. The first example that we are going to see is one way of performing data movement or data copy inside the memory without having to move the data from the memory to the processor back and forth. And this is what we call RowClone, and it's a proposal that takes advantage of the analog computation capability. Here you have some links to some relevant works in this direction. We are going to talk about them now, and some of them more in detail in later lectures. So don't worry, this is just an introduction to the, let's say, the two main trends in processing in memory: processing using memory, processing near memory. And what I want to show you is, like, let's say, two examples that I consider classic in the sense that they are, let's say, very pioneering in what they propose and have produced a lot of impact in academia and in industry as well. So the very first one is RowClone in memory copy and initialization. Why is it important? Because memory copy and initialization is used in all programs and all computers these days. So for example, from the Google study that I mentioned before, they measured that 5% of the cycles were spent on data movement or in these mem-move and mem-copy instructions. And you may think, well, 5% is not that much. In the end, if you think about one of these huge data centers, 5% is a lot of execution cycles, and it's a lot of energy, and in the end, a lot of money that could be saved if you know, the operation themselves is done in a more efficient manner. How is this operation done these days? How is in today's systems this bulk data copy, like for example mem copy, that for sure you have used as C programmers in the past? The way that this works is that if I want to copy one page residing in memory to another page in the same memory, maybe even in the same memory chip, I need to read the whole page all the way to the CPU, place all cache lines one by one of this page in the L1, and then read the destination page cache line by cache line, perform the copy here near the processor, near the CPU in the L1, and then write back. And this operation is very high latency because in order to move something that is here to another position very close to it, I have to go all the way through this memory bus, through this memory hierarchy up to the CPU. And this also entails high bandwidth utilization. This causes cache pollution because I may have in the caches data that is really useful from maybe other parts of the application or other applications. And in the end, there is a lot of unwanted data movement in this operation. And actually, it's very costly in terms of execution time. Here you have some measured for a 4 kilobyte page copy via DMA. It's like 1 second and 3.6 microjoules. If you compare these to what the RowClone proposal can enable, but essentially RowClone does is what you have already seen, is directly copying one row, one 4 kilobyte page from one location in memory to another location in memory without having to go through the memory bus or through the CPU. And this can be done with low latency, with low bandwidth or external bandwidth utilization, with no cache pollution and no unwanted data movement. And you can compare the execution time and energy of the, let's say, conventional way of doing copy to the cost of in-memory copy, and you see that we are essentially improving, reducing the latency and reducing the energy consumption by 2 orders of magnitude. How does RowClone work? It's very simple conceptually. I'm pretty sure that you guys are familiar with how DRAM operates. As you may remember, DRAM is composed by many rows, and the way we read these rows is by activating one row, in this case row A, and then moving them, transferring them to their what we call the row buffer or the sense amplifiers. Once the row is in the row buffer or the sense amplifiers, we can start reading and writing cache lines. So that's the normal operation of DRAM. So now imagine that in this situation where we have activated one row, row A, and moved it to the row buffer, now we activate another row, row B, that is the destination row. What would happen? What would happen is that we copy all the contents of the row buffer into the destination row. So this is a RowClone operation, copying one entire row to another row residing in the same DRAM subarray in a very little amount of time and saving a lot of energy, and also with a negligible hardware cost. Another question is, if this is so simple, why is not already being done in current computing systems? Don't ask me that question. This is something that it's actually feasible. It has even been tested in real off-the-shelf chips by playing with the timing parameters in the access to DRAM. It's not yet, let's say that it doesn't exist yet officially in real DRAM, but I'm pretty sure that it's going to happen very soon, because the benefits in terms of latency reduction and energy reduction are very clear. As you can see in this slide, 11 times lower latency, 74 times lower energy consumption. We will talk more about this paper in later lectures, but you can already access it by yourself and start reading, also watching or at least reading the slides as well that are available in Professor Mutlu's website. And this is the other work that I mentioned, the work that this one is not from our group. They have shown how to execute RowClone operations in real DRAM chips. The way they did it, and we will talk in detail about this compute DRAM work in a later lecture, the way they did it is by playing with the timing parameters, with the latencies that you need to respect when you access DRAM. By playing with them is possible, at least in some of the DRAM chips that they tested, is possible to perform RowClone operations. Now the thing is, okay, RowClone is nice. You can copy pages, entire pages, 4 kilobytes, very fast. This will save a lot of execution cycles and a lot of energy. For these 5% of cycles that are spent on data movement, right, on bulk data movement in Google data centers, but it's not really enough, right? It would be much better if we were able to do more operations, or more complex operations. For example, bitwise operations like and, or, not, majority operations, and do it at low cost, and do it using the analog computation capability of DRAM, which essentially is using the natural way of DRAM to work. The way we are going to do it is by activating multiple rows to perform the computation, and you will see very good performance and energy improvements, and this is what Ambit proposes. Let me very briefly explain you what's the key idea in Ambit. Is what we call the triple row activation. Is a way of doing computation with the data stored in 3 different rows, A, B, and C. To simplify here in the slide, you only see one cell, but imagine that you have a whole row, and that's why we talk about bulk bitwise operations, because we perform the operations on all the elements of the rows at the same time, which is pretty good indeed in terms of throughput and in the end performance. So imagine that in this case, we have 3 DRAM cells. As you know, a DRAM cell is essentially a capacitor and an access transistor that here is represented by these switches. We have 3 DRAM cells. 2 of them are charged, and the last one is discharged. In the normal DRAM operation, what we do is only activating one of these rows, only closing one of these switches. In this case, we activate the 3 rows at the same time. And what happens then is that the capacitors start leaking the charge onto the bit line. This bit line suffers a perturbation, and then depending on the sign of the perturbation or the direction of the perturbation, when we enable the sense amplifier that resides in the row buffer, we will have either VDD or 0 volts here in this bit line, representing 0 or 1, the digital 0 or the digital 1. So the point is, and after that, the 3 rows and the 3 cells get fully restored. But if you think about it, what is happening here is what, is a majority operation. Essentially what happened here is that we have 2 of the cells equal to 1, and 1 of the cells equal to 0. And after activating the 3 rows at the same time, the 3 of them ended up being 1, being fully charged. And this is what we call a majority operation. And the way that we can represent this majority operation in terms of and or operations is this. And this can be represented with this expression. So now, if you observe this A, B, and C, depending on what's the value of C, either if it's 1 or if it's 0, we will obtain an OR of A and B or an AND of A and B. For example, we can execute a bulk AND, which is a bulk bitwise AND, by activating 3 rows. So we would first move data using RowClone to some specific rows that are going to be those rows, let's say compute-enabled rows that can be activated at the same time. After moving the rows using RowClone to these 3 compute rows, we activate the 3 rows at the same time, and then we obtain the result that in this case is the AND, the bitwise AND of all the elements, all the bits in the rows. So this was first proposed in this paper presented or published in IEEE CAL. After that, the work was improved in the later paper, the Ambit paper, by including a way of executing the NOT operation as well. Good thing is now we have AND, OR, and NOT. And probably you guys know that if you have these 3 operations, you have a functionally complete set that allows you to create any other operation, any more complex operation like an addition, multiplication, etc., etc. The way to do NOT is by including a row or a couple of rows of special DRAM cells that are called dual contact cells that have not only 1 access transistor, but 2 of them. So if we want to execute NOT, what we do is activating 1 source row, same as we normally do. We activate the source row, then we activate the sense amplifier. So now the bit line is, in this case, charge is voltage, the VDD. And what we do next is very similar to the RowClone operation, activating another row. But the row that we activate is one of the rows of this dual contact cell that is, or this access transistor of the dual contact cell that is directly connected to the other side of the sense amplifier, of this inverter that composes the sense amplifier. So if we have 1 here, we'll have 0 here, and this 0 is copied to the destination cell when we activate this word line. So this is a way of implementing NOT. It might not be the only way of doing NOT inside DRAM, inside the DRAM subarray, but is the way that the Ambit paper proposes. And you can take a look in the next lecture and next slides at the very good performance results, orders of magnitude, throughput increase for these bitwise operations, also orders of magnitude energy savings. Do you guys have any questions?
And when you do the OR operation with the majority operation, isn't it like dangerous that you get like an undefined state because you're like in the middle of the logic level?
That could potentially happen. The fact that we are using 3 operands and these 2 operands can only have 2 different values, 0 or 1, makes that the bit line finally goes either to 0 or 1, depending on what's the, let's say, what's the majority of charge, either 0 or 1. The proposal has been tested in simulation using SPICE, as you can imagine, and it has shown enough reliability, not in all cases, of course. There is a small percentage of cases where it fails, but that might still be acceptable for many workloads. You may know that machine learning workloads, for example, are very robust and they accept some errors during the training. Even in training, in the training process, some artificial noise is added to improve the robustness and the reliability of the networks. So even though you know, these reliability issues exist in some way, but the operation is still enough reliable.
Makes sense.
Okay, yeah, thank you for the question. So I see, well, you can guys think if you have other questions. I see a couple of questions, or one question here in the YouTube chat. It says, what is meant by intra-subarray in RowClone, and what's the difference from inter-subarray in RowClone? Well, essentially, intra-subarray is what we explained about RowClone. In RowClone, we have the DRAM subarray. One of the, let's say, proposals in the RowClone paper is called the fast operation mode, where that is intra subarray consists of activating one row, then activating the sense amplifiers, and then activating the destination row. This is super fast because it happens in just very few nanoseconds, the order of 40 nanoseconds, and is activating one row and activating a destination row, and the copy is done. That's only possible inside the same DRAM subarray because these rows are connected to the same sense amplifier. Because in the end, it's useful to have more flexibility in the data movement and have the ability of moving data between subarrays or between DRAM banks. The RowClone paper proposes another technique that is called PSM, and allows this inter-subarray communication. It's not as efficient, it's not as fast, but also usable and potentially interesting for many applications. Okay, yeah, I think we can continue now. I'm going to give you an example, let's say a more, because as of now we have seen only some results for bitwise operations, but we can use these bitwise operations for more complex algorithms or applications. For example, the bitmap indices that is are used in some databases and essentially consist of performing queries on some data that resides in memory, for example, classifying let's say users of a website by their age. For this bitmap index on Ambit, we observe very good performance improvements, a reduction in the execution time of up to 6.6 times. The reason why the performance improvement is not higher is because not everything has been offloaded to Ambit. It's essentially the bitwise operations that the bitmap index application requires. But in the end, there is still some computation that is being done in the CPU. Even so, I believe that 6.6 times performance improvement is actually very good and very interesting. And this is the paper, also very recommended reading. Now you might be asking yourselves, okay, you talk about one application, bitmap indices. You have also shown some results for micro benchmarks that are just bitwise operations. But the question is, how can we enable more complex arithmetic, because more complex operations? Because as I said before, if you have and, or, and not, you have a functionally complete set. You could implement inside memory, for example, addition, multiplication, or other operations as well. Well, this was a question we were asking ourselves for a couple of years or several years. And in the end, we came up with this SimDRAM proposal that is an end-to-end framework that enables you to create arbitrary operations inside the DRAM arrays. We will cover SimDRAM in detail in a later lecture. For now, you can take a look at the paper, the presentation, the videos that are available here in these links, and I'm pretty sure that is a proposal that you will find very interesting as well. Okay. We are approaching to the end. I already covered the first of the trends of the first direction in processing in memory, processing using memory. You have already seen that it's a pretty simple approach, or conceptually simple approach, where what we do is taking advantage of the way that DRAM cells work and use them to perform data movement, to perform some bitwise operations. It's not the only, what I have explained for DRAM is not the only type of processing using memory. Non-volatile memories, for example, do processing using memory in a very similar manner. And as I said, well, in some of the cases is very similar, is let's say digital manner. In some other cases, they perform analog computation. And as I said, we will talk more about non-volatile memories in a future lecture as well. Now, the second direction or the second trend is processing near memory. And here, the example I'm going to give you is about 3D stack memories. Remember, we have multiple layers in these 3D stack designs. We have multiple layers of DRAM, and at the bottom, we have a logic layer where we can place some processing elements or some small cores. Conceptually, even though I'm going to focus on 3D stack memory proposals, conceptually, what ABMEM does with these small DPUs inside the DRAM chips, even though it's not 3D memory, it's 2D memory, but conceptually is the same. So the two examples I'm going to give you also serve as a, let's say, introduction to processing near memory and classic examples of it, enabled by the, in this case, the hybrid memory cube that remember has memory layers and logic layer. And the application that we are going to use for motivation of this type of processing in memory is graph processing. And why is that? Well, graph processing is very important in many different applications these days. A lot of information from the social networks, for example, is stored in the shape of graphs, for example, to represent the connections between users in the social network. But the problem is that all these graph processing algorithms and graph processing is pretty memory bound, and we are going to see why. The fact that it's very memory bound, is limited in the access to memory, makes that scaling graph processing is very challenging. And here you have just some motivational results for whatever graph processing algorithm. For example, PageRank 30 with 32 cores, you achieve certain performance. With 128 cores, that is 4 times more cores, we can only improve the performance by 42%. And why is that? Because most of the execution time for these algorithms, and especially for these algorithms, is spent on accessing memory. So this saturates the available memory bandwidth. Remember that the communication unit in the von Neumann model is very narrow. So the amount of bandwidth that we can exploit there is pretty small. So that's why the workload saturate. We are going to see a more concrete example. The PageRank algorithm. In PageRank, the computation is pretty simple, as you see. We have to visit all vertices of the node, and then one by one visiting the successors of this node in order to update the rank of each of the vertices. This is very simple computation, as you see, just one multiplication and one addition. But the problem with this is if your graph is huge, and that's pretty likely these days, the data will occupy a lot of memory, right? So you cannot have the entire graph in the cache. You cannot have the entire graph near the processor. So what that means is that you have very frequent memory accesses, and these accesses are going to be random. Why is that? Or let's say almost random. Why is that? Because graphs are by definition very irregular. I may have 2 friends in Facebook. You may have 500 friends. Maybe some of our friends are common. Other friends will be completely different. And all this variability makes the computation very irregular, and the memory access is very irregular. So what happens is that when you bring one whole cache line to the processor, likely you won't use most of the data in this cache line. So then you need to go again to memory and bring another cache line. So this is one key problem here. The other key problem is that I bring the data to the processor, but I don't compute enough to amortize the cost of bringing the data, because there is very little amount of computation, just one multiplication and one addition, right? So how do we solve this problem using processing in memory? We are going to see 2 classic approaches here. The first one is a coarse-grained accelerator, similar to, in some sense, to a GPU, where you can offload a whole kernel or almost a whole application and run it there and make it much faster. So here in one of the proposals that I'm going to present, what we did was designing an accelerator, coarse-grained accelerator for graph processing workloads. And the other proposal is a completely different approach. In this case, is minimal processing in memory or processing near memory support. Instead of having a coarse-grained accelerator, what we have is small execution units near the memory, and we offload the specific operations to them. And as you will see, the approach is very similar to what DRAM vendors are already doing, like this Samsung HBM PIM that we have already mentioned. And now you will see this proposal that is called PIM-enabled instructions. And then in one later lecture, we will talk in more detail about the Samsung architecture. But let's start with the other option, right? Let's start with this coarse-grained accelerator that is called Tesseract. Observe how it looks. Is here what you see on the leftmost side. It's a 4x4, so in total 16 of these cubes of these HBM stacks. Inside each of the cubes, we have the memory layers, and we have also the logic layer. What do we have inside the logic layer? We have a bunch of these blue squares that are small processors, very, very small processors in order cores that have access to the memory layers through a memory controller, and also have access to a network interface for communication with other cores inside the same stack using this crossbar network, or to other cores in other cubes, as you see here on this part of the figure. The Tesseract system was compared to different configurations of conventional processor-centric systems, like out-of-order cores, in-order cores, with DDR3 DRAM, with HMC memory, and the performance improvement was really good for several graph processing algorithms. In total, 5 graph processing algorithms that were used as benchmarks for this study. In the best case, it's almost 14 times faster than the, let's say, simplest baseline, that is an out-of-order processor with DDR3 memory, which is very similar to the type of CPU or the type of processor that we use on our daily basis. Also, in terms of energy reduction, you see 8 times energy reduction of Tesseract over the out-of-order core, the CPU, even using HNC memory that provides higher bandwidth by default than DDR3 memory, but it's still 8 times energy reduction. You can find more details in the slides and in the paper of this ISCA 2015 paper. And now the other proposal is, because, okay, you can think this accelerator looks pretty good, right? But you're using there 16 of these HMC stacks, and they don't look like a very cheap thing, right? They probably are way more expensive than the conventional 2D DRAM. Yeah, that's true. So probably building one of these accelerators is not going to be cheap. It's going to be very energy efficient, very high performance, but it might not be the best solution for all computing systems, right? Computing systems are, or we desire computing systems be cheaper, like laptops that we use, cell phones, etc. So what about providing processing in memory capabilities, but with minimal support, with minimal modifications? And that's this PIM-enabled instructions paper that was presented actually at the same time as the Tesseract proposal. For the motivation, again, we go back to the PageRank algorithm. Remember, computation is very simple, just multiplication, just addition. The problem here is that we have very random memory accesses when reading the successors of a specific node or vertex of the graph. So what this means is that we need to bring all the time cache lines from the memory, the main memory, to the host processor. And then when we don't need this cache line anymore, we have to write back the whole cache line to the memory. And this essentially means 64 bytes in, 64 bytes out. This is a lot of data movement that probably is not amortized by the computation done by these graph processing workloads. So what this PIM-enabled instructions paper, or PI paper, proposes is replacing some of these operations with operations that will be executed in the memory, in some specialized unit in the memory. For example, an addition. We can replace the conventional addition that is done executed on the host processor by this PIM add that will be executed in the main memory. And in this case, instead of having to read 64 bytes, operate, and then write back 64 bytes, what we can do is just sending the value, the number that we have to add to the main memory and perform the addition there. Good thing is that instead of reading and writing 64 bytes, we just write or send to memory 8 bytes, and we are done. And the PI paper shows very nice results for different graph processing algorithms, but also other benchmarks from data analytics, from machine learning and data mining, etc. And here you see some supported PIM operations. This is just, I mean, that say operations that were used in the PI paper to showcase what are the possibilities and what's the potential of this type of proposal, but are things that make a lot of sense for all these applications here. Like, for example, integer increment, calculation of minimum, addition, hash table probing, or histogram computation, Euclidean distance, dot product, etc. Very simple operations that are offloaded to the memory side and can be executed there faster and in a more energy efficient manner. Sometimes may happen that your data already resides in the cache, right? In the cache of the CPU because it has been used before for some reason. Well, to deal with that situation, what we can have is something like a locality monitor that essentially is a unit that checks where the data resides before executing an operation. This locality monitor essentially will check if some particular value is already in the caches. If it's in the caches, then you don't need to upload to the main memory. But if it's not in the caches, then you upload the specific instruction to the main memory. And then I can show you in this slide an example PI microarchitecture. This would be like, let's say, the baseline microarchitecture, the baseline processor with the out of order core. And here we have the 3 levels of cache, the memory controller, and the external off-chip memory. In this case, a 3D stack memory similar to HMC. The PEI architecture proposes to extend this baseline architecture with these PCUs that are the execution units near the memory or actually inside the memory stack in the logic layer, and also this PEI management unit that is the locality monitor responsible for checking if the value that I need to compute on is in the last level cache or other levels of the cache, or instead if is in memory and doesn't reside in the cache. So depending on that, I will execute the operation here or I will execute the operation there, right? The proposal results in very, say, nice performance results, not so, say, large as the speedups and energy savings that we have seen for Tesseract, because that's a coarse grain accelerator, but it's still it's pretty interesting. So here, for example, for large data sets, we obtain almost 50% performance improvement as a geomean for all these different workloads, and also energy savings quite significant as well. For large data sets, it's about 25 less energy consumption in this case. Of course, it doesn't make sense to use the processing in memory capabilities if your data set is very small, because if it's very small, very likely will fit in the cache hierarchy of the CPU or the GPU, so you don't need to go to memory so frequently. And that's why as well it's important to have this locality aware execution that can lower this large execution time of the PIM-only case for small data sets, can reduce not the execution time, this is energy consumption, can reduce it significantly. And if the locality aware monitor is let's say is well tuned and works properly, then you can get the best of both worlds, right? Whenever the CPU can compute, you compute on the CPU. Whenever data doesn't reside on the memory hierarchy, on the cache hierarchy, you go to the main memory and execute the operation there. So this is the paper for your reference, and this is almost all for today. We have already covered the 2 directions, processing using memory and processing near memory. Let me know, guys, if you have any questions from this last part. I'm reading a question I have here in the YouTube chat. It says, is not processing near memory just another iteration of GPU? GPUs have the same concept, shared memory, which is closer to thread blocks, don't they? Well, this is actually very good question, and I like that people are already thinking about the comparison of processing in memory systems to GPUs. It's true that there are some things in common. The fact that in a processing in memory system and the way that we are already describing them, what we do is identifying what computation is good for the processing in memory part, for the processing in memory system, and offload that computation to the processing in memory side. And that's also what we do in GPUs. So GPUs are external accelerators whenever we have something that is, for example, highly data parallel and can benefit from the architecture of the DPU, we offload the computation to the DPU. In that sense, they are similar. What is different? It's different the fact that the CPU accelerator, the GPU accelerator is a completely different accelerator, completely decoupled from the host processor. Discrete GPUs that are the most powerful ones are typically connected through a PCI Express bus. So what this means is that we have to move all the data from the main memory of the CPU to the global memory of the GPU. And then when you execute on the GPU, there you have a lot of parallelism, you have a very powerful device, but this powerful device also has to access an external memory, its own DRAM or global memory that in the end suffers from the same problem, the data movement bottleneck. In a processing in memory system, even if it's an external accelerator like the Tesseract proposal, and you have to move data from main memory to the memory of the external accelerator, it doesn't suffer from data movement when the computation starts on the memory side. Why is that? Because processing in memory systems enjoy much higher bandwidth, much lower latency, and at least for those applications and those algorithms that are clearly memory bound, they solve the problem in some way. That's essentially the key idea of processing in memory. Okay, I hope this solves the question. I don't know, guys, if you have any question related to that one, to the comparison to GPUs. We will see comparisons to GPU for some of these systems and for the results that we have obtained ourselves, and a good analysis of what's let's say suitable for a GPU or suitable for a processing in memory system. There is a lot to do as well in this direction. Okay, another question I see here, is it practical to have PIM core in cache? What is the area talk compared to DRAM implementation? Well, that depends, yes. So the first answer is yes, it's possible to have processing elements in the cache, and there are actually several research proposals doing that. There are research proposals that even place processing elements near the cache, but then also processing elements in the memory controller or in the DRAM chips. Depending on the characteristics of the application, they can be pretty beneficial and pretty good ideas. Also in caches, there are processing using memory proposals. There are several interesting proposals, and even some chips are being fabricated that take advantage of the analog operation of SRAM in a similar way of what I explained for RowClone and Ambit in DRAM. Something similar is also possible. I mentioned non-volatile memories, but something like that is also possible in SRAM, and there are few interesting proposals about it. So it's also, we can also talk about processing near SRAM, processing using SRAM, and all these processing near cache or using the cache proposals are also included in the larger umbrella of processing using memory or processing in memory. So yeah, I think I hope that answers the question. It's something that we will definitely discuss as well in later lectures. Okay, the last thing I have for you guys to finish the lecture, and thank you very much for your attendance and for your interest. There are still barriers that we need to eliminate in order to, make an ample, let's say, adoption of processing in memory, right? So there are things to solve, and that's why we keep doing research on that, and that's why in processing in memory, and that's why we offer these courses to teach about processing in memory and to let's say enable more people to be qualified to solve these barriers for the adoption of PIM. And here you have a list of these issues, defining the functionality for processing in memory systems, writing code for processing in memory systems, finding ways of making the programmers' lives easier, because in the end, if you have a new system, you have to learn how to program it, and hopefully the learning curve won't be that high. We need to, solve other system-related considerations, like how to maintain coherence, how to deal with virtual memory in the processing in memory system, and many other things. We will talk about all these barriers over the course of the semester. We will also have like a dedicated session to, clarify all these different barriers and the different things that we are trying to do to solve these barriers and enable definitely the adoption of processing in memory. But all these barriers can be solved with a change of mindset that requires to revisit the entire computing stack and get there step by step by changing the devices, by changing the interfaces for programmers, for the software to operate on the hardware, and also changing the way we think about the algorithms and we program them. Many of the different things that I have covered in this lecture, and we will continue covering in later lectures, and in this book chapter, A Modern Primer on processing in memory. Here you have the abstract, and here you have the table of contents of the paper that, as you know, guys, is a required reading for you for this week. This is all for today. Let me know if you have any questions. I hope you enjoyed the lecture and find the topic interesting. And yeah, I'm all ears if you want to ask. There are also a couple more questions here in YouTube. It says, it feels that the only difference is the actual copying to global GPU memory. If CPU and GPU cores have the same level of access to memory, it still feels to be the same. Yeah, maybe that's the only difference. The thing is that that difference is pretty big, and entails that processor-centric systems like current CPUs and GPUs suffer from the data movement bottleneck and spend large amounts of execution cycles and energy in accessing data. What processing in memory does, this is not proposing, let's say, a new device. This is not proposing a new accelerator. Is a different computing paradigm that can be useful for different types of devices. We can extend CPUs with processing in memory capabilities, same as we can extend GPUs or other accelerators with processing in memory capabilities. In a couple of weeks or 2-3 weeks, we will be talking about the Samsung HBM PIM that has already been prototyped and tested against GPUs, and it's designed to operate in cooperation with a central GPU. So in the end, it's not processing in memory or conventional CPUs or GPUs. Is more like improving existing computing systems by enabling processing in memory. Yes, another question is with PCI Express 6 now, it feels GPU's main copy latency would reduce drastically too. Yeah, that's true. Every time we have a new external bus, it's faster. That's true. The problem is if you compare how fast these external buses evolve and how fast their throughput, their bandwidth increases over time, that's much a slower pace than what happens with the logic, what happens with the CPU cores and with the GPU cores. Even if you go, for example, to NVIDIA GPUs and you compare G80 GPU from 2006 or 2007 and check what's its peak compute throughput and what's its peak bandwidth, you will see that the ratio between them is smaller than the ratio of compute throughput and memory bandwidth in an A100 released in 2020. What this means is that the problem is not being solved by the fact that now memory has higher bandwidth or the PCI Express also provides higher bandwidth. The problem is that even though these improve, the cores themselves improve at a much faster pace. So that's why processing in memory can help for many, many workloads. Okay, you guys in Zoom, let me know if you have any other question. If not, I think it's enough for today, like 1 hour, 45 minutes almost. Thank you very much for your questions. Thank you very much for your interest. If you don't have any other question, I think we are done for today, and I hope to see you next Tuesday.